We live in a time of unprecedented globalization, largely thanks to the existence of the digital internet. At the core of digital communication, data is transmitted through a sequence of light pulses, which represent zeros and ones. Anytime the light pulse is on, there are billions of photons transmitted, and anytime it's off, there is a gap. The next generation of communications technologies are aiming to leverage the quantum nature of light. In these protocols, instead of transmitting billions of photons, we instead send one photon at a time. Here, the zeros and ones are encoded in the quantum state of the particle, such as its polarization state. This is known as quantum communication. Using the quantum properties of photons like superposition and entanglement, quantum communication can achieve goals nearly impossible for digital networks. Quantum networks will be used for creating hack-proof communication links and connecting quantum computers and quantum sensors together. However, there's a key challenge. How do we protect the photons against loss? The loss in fiber optics increase exponentially with distance, making it practically impossible for a photon to survive in a long fiber. In digital communication, this problem is easily solvable using optical amplifiers to read and copy the incoming signals. But things aren't so simple for quantum communication. It is physically impossible to copy a quantum bit. But there's a clever solution, by leveraging quantum entanglement. The entanglement between photons typically happens because the pairs are generated together from the same source. Through the magic of quantum mechanics, it is possible to entangle photons who have never interacted with one another through a process called entanglement swapping. To perform this protocol, one photon from each pair is sacrificed in order to establish long-distance entanglement. The best thing about entanglement swapping is that we can add more and more sources and daisy-chain the process to keep increasing the distance between the two remote entangled photons. This is the core of quantum repeating. But this operation requires very precise photon synchronization across the entire network. If the photons don't arrive at all stations simultaneously, the entire process needs to be repeated. The synchronization issue is solved by introducing quantum memories. These memories hold one photon from each pair while the other photon travels to a swapping station. Upon a successful swap, the memory will release the stored photon for the next swapping step. With memories, if one block of the chain fails to swap, we only need to repeat that block. QNACT commercialized the first ever quantum memory. Our quantum memories are designed to be compatible with our entanglement source and swapping devices. Additionally, we provide a suite of products to enable the integration of these devices into telecom infrastructure. QSync is used for sub-nanosecond time synchronization between nodes in the network, while the active polarization compensator guarantees a real-time calibration of each fiber segment used for transmission in the network. Finally, our QLock provides precise frequency stabilization of the lasers across the network. All products are built in a standard rack form factor and do not require any additional cooling or vacuum support. Our quantum rack is a drop-in solution for transforming telecom fiber infrastructure into quantum secure networks, serving as the foundation for the future quantum internet.